Hi guys, this is Keshav Pranskaka and this is my lab 4 for fall 2021. The purpose of this lab was to model the motion and energy changes of an oscillating spring mass system. In this case, a mass that swings in an arc while oscillating up and down on the spring was observed. This study of motion can be used to create safety guidelines for these extreme sports. To analyze the motion of the mass and create a computational model, the momentum principle was used, while the energy principle was used to provide further insights in the energy changes that occur throughout the motion. The system was chosen as the object, the spring attached to the object, and the earth. Hence, there was nothing in the surroundings. Tracker was used to extract the position data of the mass after very small time steps, and growth strip VPython was used to create a computational model. It was found that the computational model fit the observed data quite well when using the y direction period. The position data of the object's motion was extracted using tracker. The, co- the origin of the coordinate axis was placed at the fixed end of the spring while positive x pointing in the right direction while and positive y pointing up. The length of the spring at the beginning was provided as zero point 0.7 meter and the frame rate was chosen to be 10.53 fps. From these graphs, the period in the x and y direction was calculated. The key concept used to analyze data in is the momentum principle. The principle states the following update velocity update formula, which can be used in the computer model to iteratively calculate the final velocity after each time step. The net force in that formula is the sum of all forces acting on the object, which is this case in the gravitational force and the spring force. This velocity should also be used to iteratively calculate the new position after every time step in the following position formula. Since the net force is not constant, the final velocity is used as the approximation of the average velocity. Generally, the energy principle accounts for the energy changes occurring inside the system. In this particular case, the total energy of the object is the sum of its kinetic energy, gravitational potential energy, and spring potential energy. Since the spring is considered to be massless, the change in energy of the spring is considered to be zero. The change in energy of the Earth is also considered negligible since the mass and size of the Earth is huge in comparison of the object. Hence, the change in total energy of the system can be described as its sum of the change in each of these individual energies of the system. The gravitational spin potential energies are accounted for, so we don't need to include them as a work done on the system. Hence, there is no energy transfer happening in the system. The formula on the left side were used to calculate the different types of energy present in the system, where M. From this, we can also calculate the changes in each of these energy as shown in the right hand side. The object was named, born in the code, and had a mass of 0.402 kg. Since this was the point where the object was just being let go, the initial velocity was set to zero and the time was set to zero. The initial energy for each type of energy in the slide was also set to zero. Inside the while loop and at each time step, the momentum principle was used to calculate the final velocity and position at each end of each time step. The displacement of the spring was then recalculated. After that, each energy was also calculated along with the difference in each type of energy between every two time steps. The blue line represents the computer simulation position of the system, while the red line represents the observed position of the system. Both lines are quite close to each other, which shows that the model is quite accurate. It's clear that both position graphs in the x and y direction show trigonometric function. In the x direction, as t progresses, the observed x seems to be less than the model position in that the blue line seems to be a slight stretch of the red line. Furthermore, in both graphs, the amplitude of the observed and modeling motion are slightly different. All this might be due to the fact that there's an extra force of air resistance which was ignored earlier. Another explanation for the lack of data agreement could be due to the assumption of massless spring. This is a graph of the energy graphs. The blue line represents the change in kinetic energy, the red line represents the change in potential energy, the green line represents the change in potential energy of the spring, while the orange line represents the change in total kinetic energy. However, when we look very closely, we can see that the total energy fluctuates ever so slightly, which supposes the notion that we did not account for all forces and may need to include an extra air resistance force in the code to create a more accurate model. This is the comparison between the x position using both the period found using uh, position data in the x direction and period found using position data in the y direction. They look very similar. However, when we use both period to simulate the y position, there's a drastic difference. It's clear that the period in the y direction produces results that match the observation data much better. There's a clear difference between the period found when looking of the position data in the x and y direction. However, as we've seen from the simulation, the y direction period is more accurate when simulating motion in the y direction. Hence, it's reasonable to suggest that the real period of the spring is observed based on the position data in the y direction. Realistically, the spring oscillates in both the x and y direction. However, in this particular lab, a reasonable conclusion would be that most, if not all, of the springs oscillation occur in the y direction. This could be because of the object. This could be because the object acts as a small pendulum in the x direction, in which the displacement is too small for the period of springs oscillation in that direction to have a big effect. Thank you.